Okay, so today we have Marius Tiba, who's visiting Peter. How long will you be around?
I'll be until 26.
Cool, until the 26th, and I think take it away.
Thank you very much for the invitation. I'm actually super glad to be here. It's my first time at IS. Very excited. I'll be talking about upper bounds for multicolour Ramsey numbers, and all of this is based on joint work with a large group of co-authors with Paul Balister, Bela Bollobas, Marcelo Campos, Simon Griffiths, Eoin Hurley, Morris and Julian Sahasrabudhe. Actually, one of the main reasons I wanted to put something on the board was not to forget one of the co-authors. That's one of the dangers when the list is very large. Let me start by saying that Ramsey theory is a very active research area, as you all know, and it's really about finding order in disordered systems. And it builds on this principle that complete and total disorder doesn't exist, that if a system is large, then no matter how disordered it is, it must contain an ordered subsystem. And one of the fundamental objects in the Ramsey theory is the so-called Ramsey number, which is R of k is the smallest integer n, such that every red-blue coloring of the complete graph on n vertices Kn contains a monochromatic clique of size k. And more generally, the off-diagonal Ramsey number RAB is the smallest n, such that every red-blue coloring of the edges of Kn contains either a red Ka or a blue Kb. Now, there's a long history on bounding Ramsey numbers. I just want to mention some important works. So it all started with Ramsey in the 30s, with who showed that R of k is finite. Then a few years later, Erdős and Szekeres obtained the first reasonable upper bounds. They showed that R of k is at most 4 to the k. And in general, they showed R in B is at most A plus B minus 2, choose A minus 2. And then in 47, in one of the very first applications of the probabilistic methods in combinatorics, Erdős proved the lower bound RK is at least 2 to the power k over 2. So there is an exponential gap between the upper bound and the lower bound, and this became a central problem in combinatorics to bridge this gap. And I want to mention some important results. Rodel, Thomason, Conlon, Shah, they all obtained quasi-polynomial improvements of the upper bound, so of the Erdős-Szekeres bound. But for almost a century, no exponential improvement was known for either of the lower or the upper bound. So exponentially 2 to the k over 2 and 4 to the k were best known. And a couple of years ago, in a remarkable breakthrough, Campos, Griffiths, Morris and Sahasrabudhe, 4 of the current co-authors, they actually obtained the first exponential improvement of the upper bound. So they showed that actually R of k is 4 minus epsilon to the k, is 4 to the k times some exponential of minus tau k for some constant tau bigger than 0. And actually a bit later, Gupta, Nia, Norin, and Wei, they optimized Campos, Griffiths, Morris, and Sahasrabudhe's approach, and they obtained the bound R of k is at most 3.8 to the k, which I think is the current best bound known. Now, you might wonder what happens with more colors. Well, the diagonal multicolour Ramsey number is defined similarly, so it's the smallest n such that every arc coloring of the edges of Kn contains a monochromatic complete graph on k vertices. What are the bounds on the multicolour Ramsey number? Well, an identical proof to Erdős and Szekeres just gives that RRK is at most R to the RK, and actually Erdős's random construction plus a product argument just gives that the lower bound RRK to be at least constant to the RK. So this is sandwiched between constant to the ik and I to the ik. So
Sorry.
now, in terms of the lower bound, there are some very interesting improvements. So Paul and Faber, Yuval Dickinson and Sawin, they all improved the constancy. However, in terms of the upper bound, no improvement is known over the multinomial coefficient over the Erdős and Szekeres bound, not even by a constant factor. And this is where we came into the picture. Well, I should first say, so the very clever algorithm that Campos, Griffiths, Morris and Sahasrabudhe had for 2 colors doesn't really work to extend to multiple colors. So they won by a very small margin, and if you go to more colors, it doesn't really work. Now, this is where we came into the picture. So in the formation, we followed these quarters, and using some new ideas, we managed to obtain the first exponential improvement of the multicolor Ramsey number. We showed that this is at most E2 minus some constant tau, depending on the number of colors, times I to the ik. So our improvement gets worse with the number of colors. In theory, that shouldn't happen. It should be that we get a uniform exponential improvement, but yeah, maybe that's future work. My plan for today is to give you an overview of the proof of this result. And actually, instead of jumping directly into the proof, let me try to highlight what the difficulties are and perhaps motivate some of the ideas by starting with a simple proof of Erdős and Szekeres. So let me set the stage.
Wait, Marius, before you jump into the proof. The gap is very large, right? It's between exponential and r to the r log r.
So it gets even larger as r goes.
Right. Which one is supposedly correct?
Presumably random is the correct answer, presumably.
Which is
So exponential.
The lower bound, yeah.
no dependence on our.
Yeah, so I guess also for 2 colors, I think people generally believe that random is best. But I heard Julian more recently saying he lost a bit of faith in the fact that random is best. Yeah, I'm not sure. I think random should be best or close to best. Yeah. Right, so Erdős and Szekeres. We want to prove that ik is at most 4 to the k. So let's fix n to be 4 to the k. Let's call it kn with 2 colors. Let's say 0 and 1. And our aim is to find monochromatic staking. So we are going to follow the following algorithm. And throughout this algorithm, we are going to keep track of the following data. So we are going to have a big set of vertices x, big reservoir of vertices x, and we are going to have 2 bins, one for color 0 and one for color 1. And I promise you from now to the end of time that all edges between B0 and 1 will have, B0 and X will have color 0, and all edges within B0 will have color 0. Similarly, all edges between B1 and X will have color 1, and all edges within B1 will have color 1. Now, initially, we're going to start with B0 and B1 to be empty, and X would be the whole set of vertices. And then at every step, we are going to pick a vertex B in X, and we are going to look at the most popular color in V. So let's say that the color, the neighborhood in color 0 of the side X is larger than the neighborhood in color 1 of V inside X. oops, sorry. So the picture is that this neighborhood is the larger one. Now, how we are going to update our set? We are going to put V inside the bin B0, B0 prime become B0 together with V, and X prime will become X restricted to the neighborhood in color 0. And when do we stop? We stop when X is empty. Now, what's my claim? My claim is that algorithm runs at least 2 case steps. Oh, by the way, notice that by doing this, by putting V inside B0 and restricting to the neighborhood color 0 V, we maintain this structure that all edges from B0 to X and inside B0 have color 0. Now, claim the algorithm runs at least 2 steps. That's because at every step, we go down by a factor of half. The reservoir of vertices shrinks by a factor of a half. So after 2k steps, we shrink by 2 to the 2k, which is like this one.
What about V itself?
Sorry?
Does X prime contain V or not?
Yeah, so I'm slightly cheating.
Okay.
I'm off by 1 in every count, but I don't want to keep track of it.
Okay.
Yeah, so after 2k steps, one of the bins will have size at least k, and we found our monochromatic clip. And actually, okay, if one is slightly careful and applies induction here, one can get that the general bound RFP is at most A plus B choose A. Now, the question is, can we do better? Can we beat this? Can we decrease that? And it turns out that we can in some situations. I claim that we can decrease and by an exponential factor. In some situations. Here's one of those situations. We can decrease n if in the first epsilon k steps of the process, we find some vertex V where the 2 colors are unbalanced. The red is more than yellow by a factor of 1.1. So if in first epsilon k steps, let's say in one of the colors I, the neighborhood in color I of V inside X is bigger than the neighborhood color 1 minus I of V inside X by a factor of 1.1. Because then X, instead of going down by a factor of 0.5, it goes down by a factor of 0.51. So it's not as costly. I also claim that at the opposite extreme, we have a situation where, okay, for epsilon, the first epsilon k steps, all the vertices have super balanced neighborhoods. But I claim that then, in every move, at least in the first epsilon k steps, we can choose the color we play. So we might as well choose the same color every time. But then I claim that, again, we find an exponential win. So I'm claiming that if first epsilon k steps are red, say, again, we win. And that's because after epsilon k steps, what's the situation? Well, the red bin will have size epsilon k, and X will have size n over 2 to the epsilon k. Now, if n is greater than something like 2 to the 2 minus epsilon squared, maybe that takes our number to more than 100k, I claim that this number here is greater than 2 minus epsilon k, choose k, which is like 2 to the 2 minus epsilon squared over 10 something k. So then, just by the simple Erdős-Szekeres algorithm, we know that x epsilon k will contain red clique of size 1 minus epsilon k, but blue clique of size k. So together with this epsilon k red vertices, we complete our monochromatic conclusion. Monochromatic k.
So these two observations were known 50 years ago.
Yeah, nothing new. The issue is that when you get a mix of these two, so for a bunch of steps, you get balanced neighborhoods, and then a bunch of steps maybe favoring the red neighborhood, you start playing in the red neighborhood, but then you go to some corner of the world and again you are forced to play balance. So when they keep changing, it's problematic. So it would be really nice if we had an algorithm that could force either the first thing to happen, for the unbalanced situation to happen for epsilon k steps, or to force the balanced situation to happen for epsilon k steps without them interfering with each other. So Felix, this brings me to the following algorithm. Let's have an attempt. Well, it will be a failed attempt, but let's have an attempt at actually getting an exponential improvement. So maybe I will raise my top. So yeah, let's exactly. So let me turn our attention to our main result, and let me just do it in the case of two colors for simplicity of exposition. Everything that I say will extend to one color. So we want to show that Rk is at most e to the minus tau k times 4 to the k. So here's the dream algorithm. Dream. We are still going to keep track of a reservoir set of x and two bins, b0 and b1, just as before, nothing new. But we are going to keep track of two extra sets, y0 and y1. And moreover, I'm going to promise you, as before, that all edges from b0 to x within b0 and from b0 to y will be yellow, will be red, and similarly here. Actually, more than that, we are going to keep track of the minimum red degree from x to y0 and the minimum yellow degree from x to y1. So we're going to keep track of this sort of degrees and this one. So minimum red, yellow degrees.
But not necessarily the same vertex in X, right?
So yeah.
It's not
For every vertex in V and X, I'm going to keep track of the red degree from X to Y0 and the yellow degree from X to Y1.
So
And I'm going to be interested just in the minimum overall vertices V.
of either red or yellow.
Independently. I'll keep track of both the minimum in red and the minimum in yellow, which might be different. So with that in mind, here's what I want my situation to look initially. So initially, I want my bins B0 and B1 to be empty. I want maybe X, Y1, and Y2 to have size that doesn't really matter, maybe element free. Yeah, I'm sorry, I forgot to say in the beginning of the proof. Maybe let's pick n, this number e to the minus tau k times 4 choose k for some small tau. Small tau greater than 0. And actually, I also want to insist that initially, for every V inside X, if I look at the neighborhood in color I of V inside Yi, that is 1/2 the size of Yi. But let me stop for a second and ask whether this is reasonable to ask for.
So you mean at least, right?
I actually mean equal.
Oh,
Okay. I should say that had I mean at least, I could have immediately switched to equal by just throwing away some extra edges. Because it always hurts me to throw away edges. So I might as well.
What does throwaway edges mean in edge coloring?
You're not going to use them in the final.
Yeah, I'm completely disregarding those edges. I'm never going to use them in a clip.
I see.
Okay, so, well, trivial observation. If for absolutely all vertices V in my graph, the red degree and the yellow degree are balanced, well, good news, then just take a random partition into X, Y0, Y1, you get your that the degree of every vertex V in Y0 is 1/2. For every vertex V in Y1 is 1/2. Okay, minus lil O of 1, but who cares about lil O of 1 terms? The bad news is that maybe there are vertices V that are super unbalanced. But well, wait, let's say the red neighborhood is 1.1 times bigger than the yellow neighborhood. But good news, that if while we keep finding such vertices, we can keep playing this Erdős and Szekeres moves. And if this happens for at least epsilon k steps, then we found our exponential win just by playing Erdős and Szekeres moves. If this happens for little of k steps, then after little of k steps, all of the degrees are balanced. So we can do a random partition and ensure this. Okay, we shrunk a tiny bit, but we just shrunk by an exponential of little of k. So the cost is essentially 0.
What's the random partition?
So assume for a second the situation that for every vertex V, the red neighborhood is just as big as the yellow neighborhood. Then if I take my set of vertices and just put them randomly into 3 bins.
Before this picture, you assume that the graph is balanced, so red degree is equal to the yellow degree roughly for everywhere.
Okay.
Then you partition it to 3 random classes, X, Y, 1, Y0. And then you expect to have a half red degree and half.
Yeah, then you expect from the red neighbors.
You expect that every vertex in X will have half its degree, red degree, it will remain balanced in a random partition.
I missed the logic. I thought you were assuming that the degrees are balanced, and now
Yeah,
you're
you
just.
assume that the degrees are balanced in the whole graph. In the whole graph.
Yeah, in the whole
Every partition is to 3 parts.
And it's still gonna be.
Yeah, every
And
vertex.
then what do you do?
Well, then it's just that's what it wants.
Yeah, then I'm in this situation.
I see.
Nothing yet
If
happened.
that's not the case, then you play the Erdős separation.
Exactly.
Until that happens.
Exactly.
Until it happens.
Right, and I might shrink a bit.
But it's small.
But I only shrink by exponential little of k, which is 0 cost. It doesn't matter. Perfect. So we are in this situation. What is my algorithm step? Well, here's the dream step. The dream step is that we find a vertex V inside X. And we find a large subset X prime inside X. So let's say X prime is X over 100. Such that the following thing happens. I'm going to write it down and draw a picture in a second. For all W in X prime, if I look at the neighborhood in color I of V and the neighborhood in color I of W inside Yi, those two neighborhoods are positively correlated. So that's at least one for Yi. So what's the picture? I have my reservoir set here, X. I find a vertex V. I find a big set X prime. And now if I look at the vertex W inside X prime, and I look at the two neighborhoods, so the neighborhood of V in Y0 and the neighborhood of W in Y0, so the red neighborhood, the neighborhood in color 0, then these two neighborhoods are positively correlated. So this intersection here, well, each of the neighborhoods is half Y0. If they were random, you would expect them to meet in about 1/4. I'm saying they're positively correlated, they meet in at least 1/4. And similarly, for the other one.
This you want simultaneous.
Sorry,
You want this simultaneous.
I want this simultaneously. And okay, is this reasonable? On average, if you pick a pair of random points, you would expect them that they meet in about 1/4, because each of the neighborhoods is a half. But now you actually want to have one special vertex V, so that a lot of the other vertices meet this guy in at least 1/4. So maybe it had, you know, maybe this can happen, maybe not. But if this happens, we are happy, because here's the update we'll do. So again, we are going to look at the most popular color from V to X prime. So let's say that's the most popular color from V to X prime.
Sorry, but can you, if you fix V, can't you just pick the best other vertices and then they will just, they have whatever the other vertices that will satisfy.
Yeah, but if I fix V, it might be that every single other vertex exactly misses completely this neighborhood of V. Right, so it might happen that you tell me what V is. V is this guy, it has this neighborhood, which is half of Y0. And now it might be so bad how you picked V that all the other vertices in X, the neighborhood, which is also half of Y0, exactly misses this neighborhood.
For random V and.
Well, for a random V, on expectation, the intersection is a half. But maybe it's just a super small set of vertices that are super well correlated, and a large set of vertices that are a large set of pairs of vertices that are badly correlated. So it's yeah, we'll see in a second how this can fail badly.
It's fine, it is not related to the neighborhood of V.
Right, so X prime as given by this is unknown. Yeah.
It was the same picture with the.
Yeah.
Because, no, unrelated.
Yeah, so now I want to look at the more popular colors from V to X prime. Let's say red, so let's say V inside X prime is at least one V inside X prime. And we are going to do the same move as before. So we are going to put V inside B0. And we are going to restrict X to the set X double prime, which is the intersection of X prime with the neighborhood in color 0 of V. So we are going to restrict X to this more popular neighborhood. And lastly, we are going to restrict Y0 to the neighborhood of V inside Y0.
Wait, now you're telling us what you do if you have the dream situation?
Yes, exactly. So imagine for a second that we'd have a dream situation at every step, then this is how we'd run the algorithm. Now, a couple of remarks. Obviously, if I move V inside B0 and I restrict X to the red neighborhood of V inside X prime, then we maintain this fact that all edges from X to B0 within B0 and from B0 to Y0, that they're all red. This is maintained. But actually, something else is maintained as well. So I claim that this minimum degree condition is also maintained. So let me stop for a second and explore that. So if I look now at the vertex W inside the more popular neighborhood of V inside X prime, and I want to ask, well, in the new world, what is the red degree of W inside Y0? Well, Y0, Actually, maybe I can move here. Maybe this picture is less cluttered. So in the new world, y0 prime was just the red neighborhood of V inside y0. Now, if I look at a vertex V inside X, a vertex W inside X prime, and I ask what is the red degree of W inside y0 prime? Well, because V and W have positively correlated neighborhoods, the degree of W inside y0 prime is going to be at least y0 prime over 2. So this condition here is maintained throughout the entire algorithm. Okay. So with this in mind, let's analyze the algorithm. I should say when we stop. As always, we stop when X is empty.
But just to check, in one of these steps, the size of X shrinks by a factor 200.
By a factor 200.
Yeah.
Exactly.
You are not going to use the vertices from the Y's at all in your clip.
Yeah, so I will. In a second.
This is what's called a book, or this is not?
Yeah, so a book is one of these situations where you have a set where all edges within the set and all edges from the set to the other set are all the same part. Yeah. Exactly. Yeah, so essentially in all of this, in all of this algorithms where you want to find a monochromatic clique, in essence, what you do is to construct a book and then to process that book. Okay, so here's the claim. Algorithm runs for at least 2 epsilon k steps, where epsilon is some constant much smaller than 1 over 100. 100 being that 100. Okay, why is that? Well, as Peter was saying, every step, X shrinks by a factor of 1 over 200. So after 2 epsilon k steps, X 2 epsilon k will be at least X initial over 200 to the power 2 epsilon k, which is, well, recalling what X initial was. It was e to the minus tau k, 4 to the k over 3, X was just 1/3 of the 1, over 200 to epsilon k. Apologies for the slightly cluttered thing. This tau doesn't matter at all. The point is that this is at least 3.9 to the k, this number here. And provided epsilon is sufficiently small, of course, 3.9 to the k beats 200 to the epsilon k. So the algorithm runs for 2 epsilon k steps, which means that at some point within the first 2 epsilon k steps, one of the bins B0 and B1 are going to have size epsilon k. So let's actually stop prematurely. When the max of B0 and B1 is epsilon k. Maybe let's say that B0 has size epsilon k and B1 is still a bit smaller than epsilon. So here's my second claim. My second claim is that at this stage, when we stop the algorithm, y0 final has size at least 2 minus epsilon k, choose k. Now, why is that? Well, at what rate does y0 go down? Well, whenever we perform a red move, we restrict y0 to the red neighborhood of v inside y0, which has size half. So it goes down by a factor of a half. And actually, crucially, whenever we perform a yellow move, we don't touch y0 and b0. So after epsilon k steps in color 0, y0 final goes down by 2 to the power 2 epsilon, 2 to the power epsilon k. So it's going to be n over 3 over 2 to the power epsilon k, which is 2 to the 2 minus tau minus epsilon k. Now I claim that provided tau is much less than epsilon squared, this thing is at least 2 minus epsilon k, choose k, which is again like 2 minus epsilon squared k. Okay, but then the point is that y0 being greater than 2 minus epsilon k choose k, by Erdős Szekeres, it means that we can find either by the normal Erdős Szekeres bound, it means that y0 final contains red clique of size 1 minus epsilon k or blue clique of size k, and together with this clique B0 of epsilon k vertices that are all red, it means that B0 final together with Y0 final contain monochromatic clique of size k. Right, because B0 has another epsilon k vertices whose edges are all red. Oh, yes.
What prevents you from picking like y0 or like the 0 color at every step? So you go down by like 2 to the 2 epsilon k instead of.
Yeah, so excellent question. The point is that whenever we perform a yellow step here, as we constructed the algorithm, we don't touch y0 and b0. So y0 only goes down when we perform red steps. But when we perform yellow steps, we don't touch them. Again, in a red step, what we do is we put v inside b0, we shrink y0, and we do nothing else.
So why is the number of red and yellow steps equal? Again, this
It's not. So all I said is that the algorithm can run for 2 epsilon k steps, which means that at some point, when I stop the algorithm prematurely, at some point, one of these two beams will reach a size epsilon k. Let's assume with log that B0 reaches size epsilon k. At that stage, B1 has some size smaller than epsilon k. I don't really care what size it has. The point is that there are only epsilon k steps where we kept shrinking y0. Thank you. Right, excellent. So actually, maybe to take a step back and to see exactly why this thing works. This thing works exactly because this algorithm dissociates between the two colors. So essentially, whenever we perform a yellow step, we don't touch this part of the world. Whenever we perform a red step, we increase B0 by 1 and decrease Y0 by a factor of a half, which is exactly what happens in Erdős Szekeres. So after epsilon k steps, this part of the world felt like it just had an Erdős Szekeres, it just underwent an Erdős Szekeres algorithm that jump started with all moves being red. So then we are in this winning position. Okay, so the question is this dream step reasonable to expect? So again, what do we want here? We want a big set of vertices x prime so that the vertex v and the vertices inside x prime have positively correlated neighborhoods, both in the first color and in the second color. Is that something reasonable to expect? And actually, let me simplify that question. Maybe maybe I'll raise this one. Forget about two colors. Let's say you have one color. is that a reasonable thing to expect? So here's the question. Let's say you have just a bipartite graph, right? No two colors, just one color. And let's say that it's regular with degree 1/2. So every vertex here has degree on V, X, the neighborhood of V inside Y is 1/2 Y. Does that exist? A big set X prime, does that exist? V inside X and the big set X prime inside X of size 1/100, such that the neighborhoods of V and the neighborhoods of the points in X prime are positively correlated. So for all W in X prime, the neighborhood of V intersected with the neighborhood of W inside Y is at least 1/1. Answer: no. And here's a concrete example of why this fails. I claim that there exist 1,000, let's say, sets, 1,000 of which is a number bigger than 100, famously. A bunch of these sets inside Y, such that. Sorry. So not completely disjoint, such that AI has size 1/2 Y, so all of them have size 1/2. And moreover, if I look at two of these distinct ones, AI and AJ, they are negatively correlated. So the intersection is like 1/4 minus 1/1,000 choose 2, I want to say. Times the size of Y.
1/4 minus something small.
1/4 minus something small,
This is like
depending
a
on the
code.
house. Second,
This is like a code.
exactly. And if this were the case, so if I convince you that I can construct this set, then imagine the following situation. Imagine that 1/1,000 vertices of X have neighborhood A1, 1/1,000 of the vertices of X have neighborhood A2, and so on. Well, then if you pick a vertex V, the only other vertices whose neighborhood is positively correlated with the neighborhood of V are exactly those vertices who have neighborhood A1. But that's only 1/1,000 proportion of the vertices, not 100. And it was important that this 100 was an actual constant. It wasn't important what constant it was, but it was important it's a constant. And this 1,000, I can make it as large as I want. Right, so why is this the case? Why can I construct this set? Well, let me draw a picture. So this is the set Y. Now I'm going to divide Y into parts, into 1,000 choose 2 parts. Part 1, part 2, part 1,000 choose 2. And let me put the sets here, A1, A2, A1,000. Now, each of these parts will correspond to a pair of sets. So first part to the pair 1, 2, second part to the pair 1, 3, last part to the pair 999,000. I have to tell you how I construct the sets. Here's how I construct the sets. I promised from the very beginning that A1 will have density 1/2 in each of these individual parts. Same with A2, same with A3, and so on. Now, how do I construct them? Well, look at the first part.
What do you mean in the place of this part? This is it.
So I'm going to construct an A1, which will have density 1/2 inside this part. It will have density 1/2 inside this part. It will have density 1/2.
So you have 1,000 choose 2 parts again?
1,000 choose 2 parts. Exactly. So what's the situation with respect to this part, to this first part? Well, I'm going to pick this.
No, I don't understand. I mean, I assume you label the sets by AIJ, right, by IJ.
Correct.
So A1 will have density half in only those where A1 participates.
No,
In
yeah,
all of-
absolutely all of them, absolutely all of them. Yeah, exactly. So how am I choosing, how am I dealing with the first part? Well, this part corresponds to the pair one tool. I'm going to pick A1 deterministically to be the half, to be the first half of this interval. And I'm going to pick A2 deterministically to be the last part of this interval. And absolutely all the rest of the AIs, I'm going to pick them random with density 1/2. So random density 1/2. And then I'm going to do exactly the same thing for all the other parts. So the part 1/3, I'm going to look at the cells A1 and A3 this time. A3. Now I'm going to deterministically pick A1 here to be the first half of the interval. I'm going to pick A3 to be the last half of the interval. And absolutely all the other parts I'm going to, all the other AIs, I'm going to pick them random with density 1/2. Yellow means random with density 1/2. Okay, now what's the intersection? If I do this all the way, what's the intersection between AI and A2? Well, if you think about it, AI and A2 have one part where they are completely disjoint. And in every single other part, at least one of them is random. So in all the parts where at least one of them is random, they meet in 1/4. But there is this one part where they actually fail to meet at all. So the density will be a bit smaller than 1/4 by, well, by something like 1,000 choose to.
If this is the best possible.
So I think it's an interesting question. I don't know of a better one than this one, but it would be interesting to know. Yeah.
And it's really like a binary code with distance a bit bigger than a half
Right,
and with a constant number of strings in the code.
right, exactly. Right. Right. But this spells very badly for our algorithm. Because you might say, well, okay, maybe I can compromise a bit and decrease the density. So not maintain the density exactly 1/2 at every step, but decrease a bit because some of the neighborhoods are slightly negatively correlated. But that's awful because if my density in one step drops like 1/1,000, in 1,000 steps, which is nothing in this world, my density drops to 0. So that's complete rubbish. I'm wasting your time here. However, maybe there is a silver lining, which is the following. Think about this example again. It's true that if I pick a vertex V that has neighborhood A1, all the other vertices who have neighborhood A2, A3, and so on, they're negatively correlated. And okay, the only ones that are positively correlated with V are those vertices that also have neighborhood A1, which is only a 1 in 1,000 proportion, so a bit too small. But happy things happen. Namely, these vertices who have neighborhood A1, not only that they're positively correlated with V, they essentially overlap with V. So maybe there is a trade-off between how big the set X prime we can find and how well these neighborhoods are correlated. Maybe it's a good trade-off that we find a small set X prime if we promise that these vertices in X prime are super well correlated with V. So this brings me to the dilemma of our proof. Here's the dilemma. let's say that we are in this.
Don't worry about the time, it will take a few more minutes.
Excellent, thank you very much. 10 extra more minutes would be plenty, thank you. I was already thinking where to.
Yeah, sorry, we're looking.
Yeah. So let's say we are in our usual situation. We have our set X, we have Y0, we have Y1, and let's keep track of the minimum degree. As I said, by throwing some extra edges, let's make it also regular. So let's say that if I look in color red from X to Y0, we are regular with degree B0 times Y0. And here in yellow, we are regular with degree P1 times Y1. So the hypothesis is that P0 and P1 are some numbers bigger than 0. We also have some parameters, lambda, alpha 0 and alpha 1, that I'll mention in a second. And we assume that for all V in X, the neighborhood in color I of V inside Yi has density Pi. That means exactly Pi. Then I claim the following thing happens, that it's a bit of a mouthful. Let me write it and then expand it. So then there exists a vertex V in X, and there exists a large subset X prime of X. There exists lambda greater than -1, and there exists a special color. Let me call it J. So this J is in 0 or 1. Such that the following thing happens. The size of the set X prime is at least essentially e to the minus root lambda plus 1 times the size of X. Now, for all vertices W inside X prime, we have that the neighborhood in color J of W and the neighborhood in color J of V inside Yj are positively correlated by a margin. So it's Pj plus lambda times alpha J times Pj times Yj. And in color 1 minus J, these two neighborhoods are not too badly negatively correlated. I really quite that much. Maybe let me write that again next week. Is that one readable?
Yeah, that one's fine, ladies.
Yeah, so let me put it here. The neighborhood in color 1 minus J of V and the neighborhood in color 1 minus J of W inside Y1 minus J are not too badly negatively correlated. So it's P1 minus J minus alpha 1 minus J times P1 minus J times 1 minus J.
Can you explain how it, if lambda is negative?
All the, sorry, yeah. So let me explain what happens here. So, yeah, we get to choose. This holds for every alpha 0, alpha 1, P0, P1. Now, what does this say? This says the following, that I can't promise you that I'm going to find a large set X. However, I can promise you the following. The smaller the set X prime I find, the bigger the increase in density, the bigger the correlation it is. And more precisely, I'm saying the following, that both of these, in one of these colors, the two neighborhoods are slightly negatively correlated, only slightly, by this value alpha in that color. However, in the other color, not only that the two neighborhoods are positively correlated, so this is bigger than pj squared, not only that these two neighborhoods are positively correlated, but they're by a margin proportional to lambda.
Lambda is negative than half.
Yeah, so if, for example, if lambda is -1,
Yeah.
well, we don't get to choose lambda. Lambda is given by God. If lambda is -1, then what this says is that we find a set X prime, which is a positive proportion of X, it's 1/10 X. Such that, in that case, both of these neighborhoods are only marginally negatively correlated. So both of them, in that case, both of them are slightly negatively correlated by alpha, but only slightly, just by this parameter.
Okay, so it's not always positively.
Yeah, sorry, I slightly.
Negatively, but
slightly-
not too bad.
Exactly.
Lambda is much smaller than, sorry, the
Alpha,
alpha, the
alpha is tiny.
the alphas are much smaller than tau, for example.
Exactly. Actually, we are going to apply this with alphas being like 1/epsilon k, where epsilon k is the number of steps we want to run the algorithm.
Oh,
So,
constant.
exactly. So in some sense, the density, when we decrease, the density by which we decrease is going to be like 1/epsilon k. So after epsilon k steps, we are only decreased by a small constant. Okay, maybe 1/100 epsilon k. Okay, so with this in mind, let me write the revised algorithm. Yeah, I want to keep this on the board, so maybe I move this up. And right here. So here's the revised algorithm. The initial setup is exactly the same. Nothing changed the initial setup. Now, let me pick some parameters. So I'm going to pick some parameter epsilon small. So epsilon k will be number of steps that I'm aiming to run the algorithm for. And I'm going to pick two other parameters, which are going to be, again, some constants. I can tell you, just so that they're not completely ambiguous, I can tell you what they are in terms of epsilon. It's like, sorry, epsilon squared or cubed, something like that, and lambda 0 to be something like epsilon to the -1.5. The numbers are not important, just so that they're not in complete darkness. Now, we're going to keep track throughout the algorithm, we're going to keep track of the densities between x and y0 and the densities between x and y1. So keep track of the densities p0 and p1. And we are going to apply at a particular step, at every step, apply the lemma with parameters alpha 0 and alpha 1. I have to tell you what they are. Alpha I is going to be pi -1/2 plus delta over epsilon k. So it's essentially how far away I'm from 1/2 over epsilon k. Now, there are two situations. We have regular steps and we have boost steps, depending on how big lambda is. So in a regular step, maybe let me erase this and put it here. We applied the algorithm. We have been given some lambda, we have been given some set X prime. We don't know how big lambda is. Regular steps are those where lambda is small. Regular step, when lambda is at most lambda 0. Okay. Regular steps are identical to what happened before. So in a regular step, we just look at the more popular color from V to X prime. So let's say that the color, the neighborhood in color 0 V inside X prime is bigger than the neighborhood in color 1 of V inside X prime. These are exactly the same steps we did before. So we are going to put V inside B0. And we are going to restrict X to the neighborhood in color 0 V inside X prime. And Y0 is going to be Y0 prime is Y0 restricted to the neighborhood in color 0 V. So exactly same step as before. Only new thing that I want to do is to keep track here of how the densities changes. So by how much does X shrink in that case? Well, I claim that by the lemma, we know that this set X prime that we have been given has size exponential to the minus root lambda plus 1. And lambda is at most lambda 0. So I claim that X prime essentially shrinks by a factor of e to the minus root lambda 0 plus 1 times the size of X. And I'm slightly off because I have to also restrict to the most popular color from V to X prime, so I'm off by a factor of 2. Okay, and by how much Y0 shrinks? Well, remember that we kept track of the densities in this regular graph. For the vertex V, its neighborhood inside Y0 has size P0 times Y0, so we shrunk by a factor of P0. And let me also keep track of how the density change according to the lemma. So notice that we haven't touched Y1, P1, this part of the world. So the density P1 hasn't changed at all. However, the density P0 did change. And according to this formula here, worst case scenario is that the density decreased by this alpha. So worst case is that P0 prime is at least P0 minus alpha 0. And let me perhaps emphasize for a second. We know that in one of the colors, the density went up. In the other colors, maybe it went down. The trouble is that we don't know in which color, we don't know which color is more popular from V to X. So it could be that the wrong color is the more popular one from V to X. So worst case scenario, let's assume we went down by alpha 0. Okay, but actually it's slightly easier instead of keeping track of P0 to keep track of alpha 0. So how did alpha 0 prime change? Well, according to this formula here, alpha 0 prime just changed by 1 minus 1 over epsilon k times alpha 0. So it just decreased by a factor of 1 minus epsilon k. Easier to keep track of this than of this. Okay, those are my regular steps. What about the boost steps?
If it was just normal steps, you can tolerate. I mean, this would
Well, this would be
more or less a dream case with some little.
exactly.
But also it doesn't affect tau by factor.
Exactly. So if I only get regular steps, I'm golden. That's perfect. The issue is that from time to time, we might get boost steps, where a boost step is when this lambda is at least lambda 0. Okay, so what do we do in that boost step? In that boost step, we don't really care about V. We're not going to move it to B0 as V1. What we care about is to try to get a boost in the density. So how am I going to get that boost in the density? I'm going to take x double prime to be x prime. So I'm just going to restrict my attention to x prime. I don't need to worry about the more popular color because I'm not going to play with V at all. And what am I going to do with y? Well, I know that in one of the colors called J, we get a slight boost in density. Okay, so in that color, I'm going to restrict yj to the neighborhood of V inside yj. Neighborhood of V inside yj. So let me color J. And then, how do, again, let's evaluate how do things change. So x double prime, which is the same as x prime, again, went down by a factor of e to the minus root lambda. So it's 1/10 e to the minus 10 root lambda times the size of it. Notice that here the lambda could be arbitrarily large. So before it was bounded by this lambda 0, here it could potentially be arbitrarily large. How did yj change? Well, yj prime, again, just as before, was pj times yj. How do the densities change? Well, this time we did the move exactly in order to increase the density, in order to use this slight boost. So the density went up by this alpha times, lambda times alpha j. So plus lambda times alpha j. And it's easier to keep track of how alphas change. Alpha j prime is just going to be 1 plus lambda over epsilon k times alpha j. Now, let me make a super small remark, which is the following. Notice that in one of the cases, alpha goes down by a factor 1 minus 1 over epsilon k, don't care. In the other case, it actually goes up. Point being, because the original alpha is bigger than 0, alpha stays bigger than 0 throughout this entire process. And by our formula here, that means that the density, because alpha always stays greater than 0, the density is always at least 1/2 minus delta. So always Pj is at least 1/2 minus delta. Somehow I want to emphasize this because this Pj sounds abstract. It sounds like, oh, we might allow it to drop a lot. We don't. We actually always keep it to be about 1/2. But it might go up quite a lot. So that's different. But yeah. Okay, so in the last 5 minutes that I say, if you give me, let me make the analysis of this argument, why it works. Of this algorithm, to see why it works. So there are 2 claims that we want, just as before. Claim 1, we want to, so we'll keep running the algorithm. We can keep running the algorithm until x becomes empty. What I want to claim is that we can run the algorithm for at least 2 epsilon k steps. We can run algorithm for 2 epsilon k steps. Okay. How fast does x go down? Well, it goes down by this amount, and we have 2 iterations, boost steps and regular steps. Okay, so after 2 epsilon k steps, by how much did we go down? Sorry, I said something slightly incorrectly. I meant I want to claim that the algorithm can run for 2 epsilon k regular steps. So after 2 epsilon k regular steps, by how much did x go down? Let me forget those constants there. It went down by e to the minus root lambda 0 plus 1 to the power 2 epsilon k. That is the factor from the boost from the regular step. How much did it go down because of the boost steps? Well, we don't exactly know. It's a sum over s being a boost step of root lambda s plus 1. And we don't quite know how big or small this is. Now, what we would like to show is that this is at least 1. And in a second, I'll come back to this. But before that, let me look ahead, to see what will happen ahead. So if you grant me for a second that this claim is true, then the second claim is we're going to stop prematurely. When the maximum of B0 and B1 is epsilon k, just as before. And because we run for 2 epsilon k regular steps, we definitely reach this state. Okay. Now, the second claim is that at this final stage, let's say that B0 is for 1, B0 size epsilon k. We claim that at this stage,
Why is it epsilon? Because you had the 2 epsilon k regular step.
Regular step.
B was there.
exactly. So second claim, at this final stage, we added the size of y0 is at least 2 minus epsilon k choose k. And then we can finish exactly as before, because then, okay, we can apply Erdős and Szekeres to find 1 minus epsilon k red vertices or k blue, and together with this collection of epsilon k blue ones we're done. Again, let me do a back of the envelope calculation on how fast y0 goes down. So we have a formula here for how fast it goes down in every step. In every step, it goes down by a factor of P0, the current density. And that density is always at least 1/2 minus delta. So it always goes down. Regular boost doesn't matter. It always goes down by a factor of 1 minus delta. So I claim that this is at least 1/2 minus delta to the power epsilon k. It's epsilon k, not 2 epsilon k, because it only goes down when we play a move in that color, just as before. So this comes from 1/2 minus delta to the epsilon k, come from the regular steps in color 0. And then we also have 1/2 minus delta to the power number of boost steps, which is unknown, times the size of y initially. So wouldn't it be nice if we could bound the number of boost steps and also the contribution from the sum of the root lambdas? In my final minute or so, let me just show you one line how to bound that contribution. Maybe I can right here. So what's the point? How are we going to bound the boost steps? Well, the boost steps are moments when the density goes up. It can't go too much up because at some point it passes 1. So that's how we want to coordinate it. Okay, so let's track how one of the alpha changes. Let's say alpha 0. How does it change? Well, alpha 0 final, the final one, I claim is going to be at most something like 1/epsilon k, because it's okay, P can be, the density can be at most 1, so this is like 1/epsilon k. Okay, now what's the relation between alpha 0 final and alpha 0 initial? I should have allowed myself more space, alpha 0 initial. Well, at every regular step, alpha 0 goes down by a factor of 1 minus 1/epsilon k. How many steps, how many regular steps we perform in color 0? Well, we stopped the moment that B0 had size epsilon k, so epsilon k steps. So we are down by a factor of 1 minus epsilon k to the power epsilon k, which is a constant. Now, what about the boost steps? Well, that's the point. In the boost steps, alpha 0 goes up. So this is times the product over S being a boost step. Well, in color 0, but let me not worry about that, of 1 plus lambda S over epsilon k. Now, what's the bound on, what's alpha 0? Initially, we started with density 1/2. So alpha 0 was delta over epsilon k. Or this thing here is delta over epsilon k. Now notice that this epsilon k cancels with that. So what we get is that 1 over delta is at least product over S being boost step of 1 plus lambda S over epsilon k. And now if I take a log factor, I get that log 1 over delta is at least sum over lambda S over epsilon k. So this altogether means that sum over lambda S, where S is a boost step, is at most log 1 over delta times epsilon k. But if we can bound the number of, if we can bound the sum of the lambdas over the boost steps, given that we only play boost steps if lambda is at least lambda 0, then we get a bound on the number of boost steps. So this means that the number of boost steps is at most log 1 over delta times epsilon k over lambda 0. That's the number of boost steps. And we can actually also bound the sum of this contribution here of root lambda I. And for that matter, in order to bound this contribution, we didn't actually need it to be a square root. Any power smaller than 1 would have been just as good. So yeah, it didn't really matter. And we can bound this by log 1 over delta times epsilon k over root lambda 0. Again, because of all the lambdas are greater than lambda 0. But now, okay, I don't want to waste more time. Now just plugging the values delta and lambda zeros to be this one, we get exactly what we want. We get that this contribution here is negligible compared to this one, and we also get that this contribution here is negligible compared to that one. So we just get exactly what we want. Okay, I'm going to stop that.
Thank you. So any questions?
So what's new in this approach? I think the second paper with the optimized constant for 2 colors uses embedding on the sphere and low dimensions. You forget all about it.
No. So this is this lemma here, this key lemma here. I haven't told you the proof of it. What I can tell you is that maybe I can erase this part here. Yeah, what I can tell you is that this is a geometric lemma in disguise. And the geometric lemma is actually very simple to state. So an immediate translation by changing from neighborhoods to indicated functions transforms that lemma in this geometric lemma here. So let's say V1, V2, Vn. Actually, maybe let me call this M. Vm, W1, W2, Wm. And vectors in Rn. The ambient space doesn't matter at all. It's any Hilbert space. Then there exists lambda greater than -1, such that the probability that either something happens or something else happens like this. Either the probability that over I and j that unit product of Vi, Vj is at least lambda, and unit product of Wi, Wj is at least -1, that this probability is e to the minus root lambda plus 1, or the same thing with V and W interchange. So Wi, Wj is at least lambda, and Vj is at least -1, is at least e to the minus root lambda plus 1. So this geometric lemma is the key motor that makes the key lemma work. Yeah, as it happens, this also has a very, very short cute proof.
The key lemma also have short cute proof or not?
Sorry, the key lemma is the proof. The key lemma is an immediate translation of this one by switching from neighborhoods to indicated vectors. Yeah.
And for more colors than two?
Right, so this proof, as I stated, was for two colors. It works identically for more colors. The only cost is that the more colors you have, the worse the constants in here you get. And that in turn forces the gain, this tau in the beginning forces it to be smaller and smaller. But it shouldn't be. I mean, realistically, we should get a universal improvement.
You think the lemma can be improved or some other moves need to be made?
So probably the lemma as well can be improved, the key lemma as
Can you
well.
say something about it? Like, is there some geometric way you can explain how the vectors can be?
Yeah, so yeah, what's the situation here? So here's the story about this thing. Maybe let me erase this. So how how do we visualize this lemma? Well, here we have two sets of vectors. Let's say that I just have one set of vectors. And I ask you the following. So I just have vectors v1, v2, vn, in vm's, right, in IN. And I ask you for the following question. What is the probability that, let's say, vi, vj is greater than 0? So can we lower bound this probability by something? Well, it turns out that we can for the following reason. From any d+1 vectors, from any n+1 vectors in Rn, there are two vectors that have positive unit product. So n+1 or n+2. Maybe I'm off by one. From n+2. From n+2, because the simplex would have n+1 like this. Yeah, so from any n+2 points, we have two that have positive unit product. So this gives a bound on this probability. But now you can ask the following thing. Let's say I have a bunch of pairs of vectors, v1, w1, v2, w2, and so on. So imagine that all of this come in pairs. Then question, can we also bound the probability that not just one of these things happen, but they happen simultaneously? So the probability that this inner product is greater than 0 and this inner product is greater than 0. Can we lower bound it by something? And it's not known. We don't know this. But what this lemma says is something close to that. Namely, it doesn't give a bound on this probability, but it says either we have a lot of vertices that have positive unit product or not too negative unit product, or we find a small collection of vertices whose unit product is large, is at least lambda. So it makes a dichotomy. But I think this is a problem that would be interesting on its own. So for this one, we have a probability like 1 over n, whatever it was, 1 over n plus 2, whichever it was. What is the correct thing here? Is it true that this probability is 1 over polynomial in n? Something like this.
What is the proof of the first thing? Is it, I mean, if it's easy to say.
For this one, or you mean?
The 1 over n plus 2.
Yeah, so, okay, yeah, it's a super simple proof that shows that from any n plus 2 vectors, you have two that have positive unit products. That's because from any n plus 2 vectors, you can divide it into two groups, group A and group B. So that if you look at the convex hull of group A and the convex hull of group B, these two intersect. These two convex hulls intersect. So let me explain what.
Like a linear combination,
Yeah.
split the coefficient.
Sorry, n is the dimension of the space, not
And is the dimension of the space.
Okay.
Yeah, exactly. You write a linear combination and you split in positive and negative. But the moment that happens, it's the moment when you know that the unit so there exists a point which is an affine combination of group A, which is also an affine combination of group B. So if you take the unit product of this affine combination of A and the affine combination of B is positive. But that means at least one of the unit products is positive as well.
Any more questions? Maybe we can take it to lunch. Okay, thank you.